Great. So now, see, one thing is, remember, a transistor basically responds by pushing a current. And where does the current flow in a transistor? Between which terminals? Drain and source. So essentially, a transistor responds by pumping out a current between drain and source, or source to drain. And this current is in response to what voltage? Majorly gate to source voltage. So in a way, I can think that my input is this is my cause, and the output effect is observed here. So which means I can basically apply input at the gate and see what happens at the drain. That is one possibility. I can also apply an input at the gate and see what happens at the source, or I can apply input at the source and see what happens at the drain. So we'll have three different possibilities. So as of now, we have seen only this, where I applied input at the gate. So how much small signal voltages I get at the drain. For the sake of completeness, let's also experiment with the transistor and see what will happen if I do the other combinations. So right now I'll consider this case. I'll apply input at the gate and see what happens at the source. So I'll just draw the small signal picture first. So this is my transistor. We'll make it smaller. I want to apply a small signal voltage at the gate and see what is the corresponding small signal change I see at the source. Fine. And in this endeavor, I will try to keep the drain voltage to be fixed. Right. That is, when I'm checking input at the gate and trying to find the voltage at the source, I'll keep drain as my reference potential. So which means for small signals, this will be my ground. Yeah, this is only for small signals, right? For small signals, it is ground. Drain voltage is small signal ground. Okay. And if you didn't know, this is what we refer to as common drain, because now drain is my common potential. I'm measuring everything with respect to that. Okay, so this is only the small signal picture. Let's see how the total circuit should look like. So I'll have something like this. Drain must be small signal ground. So in the actual circuit, where will I connect this to? A DC voltage source, and for an NMOS transistor, drain is at the highest potential. So I'll basically connect it to VDD. And I'm taking the small signal output from the source. And for small signals, I want this to be an open circuit like this. So what can I connect here? A current source. Okay. Some I0, let's say. And at the gate, I'll have the small signal B in, to which I'll add a DC bias. Right? I'll not show the biasing. At this point, I'm sure you are comfortable how to add the DC voltage to the small signal. And of course, this is what we saw last, right? The constant current biasing, where I sense the current at the source and change the source voltage. So this is basically biased with a constant current. So biasing is set. Now I'm trying to see if I make changes at the gate voltage, what will be the change I see at the source voltage. And for starters, I'll ignore R0 for the transistor. And this is something we should typically try to do. Anytime you have a new circuit, don't have all possible non-idealities and sort of try to solve. Assume things are ideal and try to get a feel for what's happening in the circuit. Then you can start to include non-idealities one by one and see what happens. Right? So again, let's assume R0 to be infinity. So my question is, there is a DC bias VB. Along with the DC bias, there is a small change in the gate voltage. So if let us say the gate voltage changes by V in, how much will be the change at the source voltage? How much will it be? 0 V in what? V in. Why? Yeah. See, this is what we saw with the biasing also, right? See, what is the total current flowing in the transistor? Will it change if I change the gate voltage? Why? The current source is sitting there and making sure that the transistor is biased at the same current. So which means if I change my V in, change the gate voltage by V in, how much will be the change I see at the thing here? That will also increase by the same V in, so that the VGS is fixed. Please remember, I have ignored R0, which means the current only depends on what voltage? VGS. R0 is infinity, so the current does not depend on VDS. It only depends on VGS. If the current has to be constant, VGS has to be constant. Which means if the gate changes slightly, the source will faithfully track the same change to make sure that the VGS is constant. Is that clear? So which means, for example, if I look at the total voltage, if this was VB here, let us say at the source, I don't know, I'll call it say VC. The DC voltage I see is, let us say, VC. If the voltage changes by V in, this voltage will become VC plus V, to keep the gate to source voltage same. Is this clear? So of course then looks like the small signal gain. How much is the small signal gain? So that begs the question, why do I want a thing that has a gain of 1? Buffer? What's a buffer? Sorry? YouTube video is buffering, that buffer. Okay, probably you guys know, if not. Yeah, I'll just briefly say it, right? See, the idea is this. Let us say you have, let us say, some signal. Let's say you have a voltage source, right? And typically it will have its own source resistance, say RS. Now let us say you have a load and you want to make sure that this voltage is sort of delivered to the load. If I directly go and connect it, what will be the voltage I see across the load? RL by RL plus RS times V in, right? So if my load is very small, or my source resistance is much larger than my load resistance, only a fraction of V in will get will appear across RL. So that's where we try to have something in between. So we try to put a voltage buffer that ideally has an infinite input resistance, so that the entire V in here gets dropped across this fellow, and then you sort of copy this voltage and provide it across R. So voltage buffer is what kind of a controlled source? Voltage control? Voltage source. Right? So this will be with a gain of 1. So which means, since I am sensing the voltage here, the input resistance of this voltage buffer must ideally be infinity, or very, very large in practice, so that the entirety of the signal is dropping across the input of the buffer. Similarly, what should be the output resistance of an ideal VCVS? 0, because remember, I want this to act like a voltage source at the output. A good voltage source will have ideally 0 output resistance, or let's say, but in practice, let us say a small R out is there. As long as R out is sufficiently small, you are okay. But again, small, large, they are all relative terms. So in this particular example, how small should R out be, so that doing this is better than doing this? I know R out should be small. My question is, how small should R out be, or relative to what R out should be smaller? RS or RL? There are only two resistance. R? L. Why? I'm saying compared to this, if this should be better, what should be the comparison it should be? Okay, here what is the output voltage I get? RL upon RL plus R out. So I want this to be closer to 1 than this fellow. So R out should be smaller than what quantity? RS. Is it clear? So at least in this situation, if I ask you this question, that this should be better than this, what is the limit on R out? Yeah, R out should be then smaller than RS. And ideally you want this to be equal to 0 or like as small as possible. Okay. So let's verify what is the input and output resistances for our circuit. What is the input resistance here? Infinity, because gate does not draw any current ideally, right? So which means input resistance is infinity. We are good. So let's try to find what is the output resistance. So let me just copy this. So if I were to write it again, my Rn is infinity, that is clear. Because I am looking into the gate draws 0 current. Now I am trying to find the output resistance. Again, it's a small signal output resistance. How will I find the output resistance? This is my output side. How will I find the resistance? It is same thing. Draw the small signal equivalent and apply test voltage and check. So if for small signals, VDD is ground, current source is open, right? And I'll make sure no other signals are there. So this is grounded. So I'll apply a test voltage. Again, we have ignored R0, so make it simple. So what will be the current drawn? I test. We just saw it few minutes back. This will be. Is that fine? Because for small signals, transistor is going to behave like a voltage controlled current source. So it will pump out a current, which is Gm VGS. This is equal to minus Gm VT, which means the current that will flow in this direction is plus Gm times Vt. So that is my test current. So what is R out now? Okay. Okay. So now, we had made our life simple by ignoring R0. Let's include the effect of R0 and repeat the calculation. So same circuit. I am trying to include the effect of R0. This is with R0. Okay. So this is my. So again, usual procedure is this. Again, you draw the small signal equivalent. Use KCL and find it. But we'll try to do something different, and this is something we will do quite often in the rest of the course. And the ideas are following. See, for small signals, this is a linear circuit or a non-linear circuit? Linear circuit, right? That's the whole point of doing the small signal approximation. Now, if we have, let us say, any linear network, okay, let us say we are exciting with some input voltage. I don't care. I am only interested in the behavior across the output port, let us say between two terminals. So how can I basically model a linear network simply? The simplest way to model a linear network across two terminals, what is that? Thevenin equivalent, which is what? Voltage source in series with a resistor, or current source in parallel to a resistor. And we'll stick to current source in parallel to R out because that becomes slightly more practical. This is your Norton equivalent. Yeah. So basically, if I call this as, let us say, 1, 2. So basically, if I have this or this, if you don't have access to the inside portion of the yellow box, both will behave the same. Okay. And how do you find this Norton current? Let us say you have the network. Yeah, let me just take this. This is my network. So I basically go and short the terminals. So which means the entire current flows here. So whatever current you measure when you short the terminals is the short circuit current, the Norton current. So that's why I'll call this the short circuit current. That is essentially a Norton current, nothing fancy. And the this Thevenin or the Norton resistance is effective resistance seen across this port, that I'll call as the output resistance R out, because that is essentially the resistance seen across the output port. So instead of calling it as a Thevenin or a Norton resistance, I'll say it is the output resistance, the effective resistance seen across that port. Fine. So which means if I were to find the output voltage for any linear network, I can basically do this experiment. I'll find the short circuit current, multiply with the output resistance, that will give me my output voltage. Okay, this clear? The same thing as a Norton equivalent circuit. And in our particular example, remember we have some output voltage because there is some input Vin exciting this. Correct? So if I measure the short circuit current, that should come because of Vin. Correct? And this is a linear network. So how will the short circuit current be related to Vin? Yeah, it's a linear gain, so we'll call this to be some GM. It's a linear network, so the input output quantities will be related in a linear fashion, and the proportionality constant is what we call as GM. So which means if I look at my total V out, it is my short circuit current times R out, and the short circuit current you will have because there is some Vin in the circuit, right? That's what I'm writing. This times R out. So which means my gain I can compute as GM times R out. Okay. And remember, to find this GM, what I'm doing is the following. I'm shorting my output, measuring the current, and dividing it by the input voltage. That's all. Right? So this is typically called the short circuit transconductance. Okay. So the bottom line is this: if you have any linear circuit, we can find the voltage gain or the output voltage like this. You first find the short circuit GM, that is, you small signal short the output, measure the current, and then you divide by the input excitation, that gives the short circuit GM, and then you find the output resistance, take the product of the two, you will get the gain. And I mean, this becomes much easier because see, moment you are shorting your circuit will be simplified, so calculations will be much easier. That's one reason why we do this. So let's try to apply the same for this circuit, but before that, is this point clear? Right? I'm just reusing whatever you knew about Norton circuit. The Norton equivalent circuit is what we are exploiting again, just giving it a different name. Okay, so now let's do this. So this is, I'm including the effect of R naught. So first let's find the short circuit GM. So I'll draw the small signal equivalent. So drain is incrementally short. So here I have V in, and the current source is open, and this is my output side. And for finding the short circuit GM, what will I do to the output? I'll short circuit it, that's why it's called short circuit GM. Basically, I'll short circuit and measure the current flowing here, that's all. Okay, so let's calculate. Again, for small signals, I'll model the transistor as a voltage controlled current source in parallel with the resistor R naught. Again, this is a dependent current source. I'm not drawing that diamond symbol and all. And what is the value of the current source? GM VGS. What is VGS here? V in. Fine. Now look at R naught. One end of R naught is connected to small signal ground. Other end of R naught is also connected to small signal ground. So is it playing any role? So I basically can remove this. basically say this one. Right. So I'm interested to measure the short circuit current ISC. So what is the short circuit current? Minus or plus? Plus, minus. I mean, I have the current flowing down, the same current is going to flow through the short circuit. So it is the same sign. So which means what is my short circuit GM? Capital GM. It is the operating point transconductance GM of this transistor. So, okay. So let's do R out. So again R out, I'll draw the small signal picture first. I'm trying to find the output resistance here. So again I'll apply test voltage, and as usual the transistor I'll replace it like this, R0 and this. What is the value of the current source here? Minus GM times V test. So I'll again once again flip this and say this is plus GM V test. Right? I mean, we already knew if R0 was not there, what is the output resistance? 1 by GM. Now look at R0. So and tell me how is R0 connected at the output. I mean, what I'm saying is if R0 was not there, I knew the resistance was 1 by GM. That much is clear. Now I look at R0, right? Maybe I'll draw in a different color. So I see that R0 is connected across these two terminals. That is, one end is connected to the output terminal. What is the other end? Ground. So what is effective resistance now? So R0 is basically connected in parallel to whatever impedance you had. The earlier impedance you already computed as 1 by GM. You add an additional resistance R0 in parallel. Is that clear? I think that's about it. So the gain is basically short circuit GM times R out. So this is GM times 1 by GM parallel R0. And if you sort of simplify it, you might get something like this: GM R0 by 1 plus GM R0. This I just written the product. I mean, that's not relevant. Okay. Right. Okay. So one thing is, see here, I am trying to measure the short circuit GM, right? So let us say in lab you want to measure this short circuit GM. So this is my actual circuit. What do you do to the output? Will you connect it to ground? Do you connect it to ground like this? Yes. If you connect it to ground, what will happen to the operating point conditions of the transistor? It will get screwed up. Remember, I am basically finding the short circuit GM, but I am looking at small signal pictures here. So when I am short circuiting this, I am basically saying for small signals it's a short circuit. Okay. So if I have to actually go and measure this, what will I connect this to? You put a voltage source of that same operating point value. Right, so which means, let me iterate this because another common point of confusion is this. If I had to go and measure this, my actual circuit will look like this, right? So I'll have VDD, I have the bias voltage plus a small signal input I apply. It is biased with the constant current. Now for small signals, I want this to be ground and measure the current flowing through the small signal ground. So I'll go and connect this to a voltage source of the same value, right? If let us say the operating point voltage was some VC, I'll put a voltage source there. All the small signal currents will basically flow here. So this is where I'll measure the short circuit current. Is that clear? Because when I say I'm finding the short circuit current or short circuit GM, I'm merely referring to the small signal short circuit. It is not as though the actual node there is connected to the hard ground. Awesome. And yeah, the resistance, the output resistance as we saw is 1 by GM parallel R0. So few more pointers on that. But before that, this calculation or explanation is clear. Okay. So yeah. Fine, let me move on. So let me summarize. So if I have this, as we saw, the looking resistance, equivalent resistance is, how much is this? 1 by Gm. With R0, how does it change? Okay, question to you. Now, is the resistance equal to 1 by Gm parallel or not, only in saturation or even in linear region? Question is, I am finding the output resistance and I am saying it's 1 by Gm parallel or not. The question is this value, or is this expression valid only in saturation or even in linear region? Remember that again, for small signals, a transistor is always a voltage controlled current source parallel to R0, irrespective of the region of operation. Right? This is something I have been iterating from the first few classes. That will change. Yeah, that's okay. But the expression is still same. Right? So this model is always valid. As we pointed out, what will change is the value of Gm and value of R0. Okay. So the actual output resistance is this, but yeah, as you told, Gm value will change, R0 value will change. Because Gm, R0 are essentially your Y21, Y22 that you compute at the operating point. Yeah, expression remains the same. And if it is in saturation, you already know my intrinsic gain is Gm R0. This is greater than 1. So which means R0 is much greater than 1 by Gm. So how can I approximate this in practice? Okay. I have a very small resistance in parallel with a very large resistance. The smaller one will dominate. So I can always say this approximately 1 by Gm, provided it is in saturation. Okay. Okay, so now another question to you. Maybe. Yeah. Okay, so now remember you had this setup, the diode connected transistor. Again, if I ignored R0, what is the small signal resistance of this? That was also 1 by Gm. Now again, if I include R0, R0 will be connected from this node to ground. This will become 1 by Gm parallel R0. So stare at these two and tell me, does it make sense that, if this is 1 by Gm parallel R0, without computing I can say that this is also 1 by Gm parallel R0. How can you say? Yeah, I'm sure you are appreciating. See, remember, the moment I have this, I know this is equivalent to a resistor with the value 1 by Gm parallel R0, or roughly 1 by Gm for saturation, right? Now it doesn't matter if I basically, let me copy this. So I'm hoping this point is clear. We established it well in advance. One port nonlinear network is always equivalent to a resistor. Now it doesn't matter if I short this and find the equivalent resistance looking here, or basically short the other terminal and find the effective resistance looking here. Is this fine? So even without having to compute the looking in resistance into the source, from this information, we should be able to easily deduce that the resistance looking into the source in this case is also roughly 1 by G. Because effectively I have a resistor, I don't care whether I ground this terminal or this terminal, the resistance is still the same. Okay, great. So which means if I have something like this, the looking in resistance is roughly 1 by Gm. And one thing to notice, the resistance looking into the source, it is not always 1 by Gm, especially if you have a resistor connected at the drain side. Okay. I have RD. Okay, I mean that should be obvious from this, because we already know that if only gate and drain both are shorted to ground, it is 1 by Gm. The moment I have RD here, these two will be at a different potential. so we cannot say. So only if gate and drain are roughly at the same potential, you can say that it's 1 by gm, correct? So which means for small values of RD, do you think this will be 1 by gm? For large values of RD, it is 1 by gm. Remember, my drain should be as close to small signal ground as possible. So as long as my RD is sufficiently small, I can make this claim that it is still 1 by g. Again, this is for, let us say, small RD. Again, small, large, again they are relative terms. Here it turns out RD must be much smaller than R0. Then this turns out to be correct. So in fact, I will give it as a practice problem for you to work out. Exactly calculate the equivalent resistance looking here, considering the effect of R0. Okay. Just apply the same. Apply a test voltage, find the test current, take the ratio. I will not do the algebra in class. You please work it out, just as a practice, and then you will get it. Okay. And in fact, in the limiting case, let us say RD is very large, right? So which means I will take RD to be infinity. RD is infinity, which means for small signals, I have an open circuit like this. Or in other words, for small signals, it is open circuit. So in the large signal picture, what should be here? Should be a current source. So in the actual circuit, let us say I have a current source like this. Maybe I'll draw that also. So what I'm saying is, let us say I have a current source like this. This is connected to a bias voltage, and you are trying to find the equivalent resistance. Which means in small signals, the current source is open, the gate is incrementally short. This is what you have. So again, I'll do the same thing. I'll apply a test voltage, find the test current. For small signals, it is basically a voltage controlled current source. This open circuit. So how much will be the small signal test current in this case? Will you be able to tell me by inspection? GMBT. Why? Okay, what can you say about the current flowing here? If I call it IX and current IT. IX and IT will be same. What is IX? Why? Open circuit, no current flows. IX is 0. So what happens to IT? Clear? So in this case, so what is the equivalent resistance? Infinity. I mean, of course, you have this GMBT current, but that will basically circulate within R0 itself. None of this current will come out here. Because remember, current requires a closed path to flow. If you make sure this is an open circuit, no current flows. So which means don't blindly always think that the resistance looking into the source is always 1 by gm. It is indeed a strong function of the drain resistance. Maybe I'll even give the expression you work out. This will be something like this: RD plus R0 by 1 plus gm R0. Okay. But you work out and see. Later we can understand why this intuitively makes sense. So which means the equivalent resistance is approximately 1 by gm if my RD is much smaller than R0. Which means if R0 is infinity, what can you say from this expression? If R0 is infinity, this will dominate and this term will dominate. We can always say it's 1 by g. So only if you ignore R0 completely, or the drain resistance is much smaller than R0, you can say that it is 1 by g. This result is something we'll use quite often in the rest of the course, so please make sure you understand it. Okay, great. Okay, so we are looking at this common drain. So there is another variant of common drain. Let me show. I don't have this copied. Yeah, this is my common drain that we have been looking at. So quite often in practice, we, let us say, don't want to use a current source. I first look at the operating point. Let us say this is VB. This is, let us say, VC. This is the operating point picture. I want to make sure that I want to see if I can have a resistor here in place of a current source. Again, this was a problem in your practice set, if you already saw. So my question is, or my point of thought is, instead of having an ideal current source, can I get away with a resistor here for the bias point alone? Or other question is, other way to ask is, what do you think should be the value of Rs so that the transistor is biased at the same, source voltage Vc, biased at the same current I0. Of course, you can solve for the circuit and then do this, the current is half mu and Cox W by L Vgs minus Vth whole square. Solve this and find it. But by looking at these two circuits, will you be able to give me what should be the value of Rs? Huh? Sorry? Minus Vc. I don't have a negative resistance. Okay. Vc by? Why do you say that? Okay, remember, let us say, I want to make sure that the this voltage here is Vc, correct? And I want to make sure the current is I0, right? So which means, sorry, what happened? Yeah, hold on. Yeah. So which means I0 is essentially what? So if I choose my Rs to be the same voltage as I0, and okay, remember, this is basically inverse of substitution theorem. Substitution theorem says if I have a resistor, as long as I keep the same voltage and current across it, I can replace the resistor by an equivalent current source. I can replace a resistor by an equivalent current source. Value of the current source should be the current flowing through the resistor. Then the circuit will have no idea what happened. For all that it knows, the same current is getting pulled out. KCL has to be satisfied, so the voltage will remain the same. It doesn't matter whether you have a resistor or a current source. With respect to KCL, what do you want? I want to make sure sum of all the currents is 0. As long as I make sure the same current flows here, both are equal. So anyway, so let us say now we have something like this, right? This is now your common common drain. So instead of a current source, I have a resistor like this. Let's see what happens. But is this clear why we are doing this? How we are doing this? In fact, in practice, when you design things on chip, you have, current mirrors like this, right? On chip, we'll have multiple, copies of current, multiple transistors mirroring a reference current, and this will be a reference current that will be provided outside. This will be your pin. So you push in a reference current to your chip outside the chip, and all the currents will be generated and mirrored from this. And even here, we don't use a current source. Instead of a current source, you go and put a resistor of appropriate value. Then you'll have the same current flowing, and this is how we typically do, because current sources are not there. So anyway, so now let's actually get back to this. So this is my common drain. I'm looking at small signal pictures now, so let me just draw the small signal picture. Drain is incrementally short. I apply small signal V in here. I want to find small signal V out. Again, we'll first ignore R0 and first find out what is the output, and then include R0. So we'll go by the root of short circuit GM times R out. So again, we'll try to do the same. I'll short circuit my output. What will be the current flowing? If I short circuit this, what is the source voltage? What is the small signal current? GM times? Okay, if it's not, I'm short circuiting this. Source voltage is 0, gate voltage is V in. This will push in a current of GM B in. What is the short circuit GM? How much is the short circuit GM? It is the operating point GM of the transistor, GM, right? Where is this? And now what is R out? Looking here, I have something here and something down. What is the resistance looking down? I have RS connected, so that is going to be there. That will be in parallel with whatever resistance I have here. How much is that? Remember, the drain is incrementally short, so which means I can always say it's 1 by G. I mean, that's why you prefer to do it this way, because otherwise you write KCL, draw small signal, write KCL and solve it. This is more intuitive. As long as you know what is effective resistance looking into each nodes, and short circuit GM is typically easy because you basically sort of short things. Is this clear? And now let us say you include R0 also, right? So let me say with R0, what will change? Do you think my short circuit GM calculation will change? I'm shorting this. R0 will be connected across this. Will R0 come into picture? No, because again R0 is connected between two grounds. So R0 will not affect my short circuit GM. Is that point clear? So I'll not draw this again and again, I'm just showing it. If it is not clear, let me know, I'll explain again. So for short circuit GM calculation, my R0 will not affect, because as you see R0 is connected between drain and source, and both of them are small signal ground. Right? It is as though the resistor is not there at all. So this is still the same. Let's see how R out changes. Again, for output resistance, R0 is connected like this. So how will the expression for R out change? Again, you see R0 is connected from the output terminal to ground. So it is as though along with RS, I have another resistance put in parallel. So that becomes. Is this clear? So I will not be doing calculations, like from scratch. I will try to give explanation like this. So please make sure you are comfortable with this. If not, feel free to stop me. I will explain again. Because in your first circuits course, you would have done all with KCL, KVL. Now it's time to step up. So we'll try to do it by inspection like this. Great. So which means my gain now is GM times R out. Right. Again, if you solve for this, I'll just give the expression. You will get something like this: GM into RS parallel R0. This is just algebra. So trust me, this is what you will get. So let us say you get this expression. So I mean, anytime you solve something and get an expression, stare at it for a moment and see if it makes sense, and try to understand this. So one sanity check you should always do is try to see if it's consistent with respect to dimensions. So I'm trying to compute voltage gain. What is the units of gain? Dimensionless, voltage by voltage. So is this quantity dimensionless? Fine, at least sanity check is done. Now let's try to understand if for some special cases we can predict the result. Is there some special case of RS and R0 for which we already knew the result? Is there any special case of RS and R0 for which we already knew what the gain was? I mean, remember when I had an ideal current source? Yeah. When I had an ideal current source, without calculating, by logic we could say gain was 1. So which means R0 was infinity and RS was also infinity. So which means I already know if R0 and RS tend to infinity, this should tend to 1. Is that happening here? Right? This fellow tends to infinity. So which means numerator this will dominate, denominator this will dominate. This limits to 1. So at least one more check is done. Now let's try to make another observation. If I make Gm to infinity, what happens to the gain? That also becomes 1. So this is a new observation. Let's try to understand why this makes sense. Okay, so why does it make sense? That is, I see that if Gm is infinity, irrespective of R0 Rs, the gain should approach 1. Why is that so? Any guess? Okay, think of it this way. Any inputs from your end? No? Okay. So what is the small signal current pushed by the transistor? Gm times? Gm times? Is it Vin? Gm times VGS. The gate voltage is what? Source voltage is? I know for a fact all the voltages in my circuits are finite, which means the current has to be finite. Right? And I am tending this to infinity. So if the current has to be finite and Gm is infinity, what should happen to this quantity? That should tend to 0. Right? Of course, I am not showing a proper mathematical limit explanation, but should make sense. Right? So which means Vout must be equal to V. Is this clear? Remember, this is the same thing as what you learnt as virtual ground in op-amp. So let us say this is ideal op-amp, which is what we are trying to build. Let us say you already had an ideal op-amp and do this. If this is V in, the gain is A. This is V out. Let me see if I can make some space. Yeah, so what is V out now? The output of the op amp is the gain times the non-inverting minus inverting terminal. This is A times how much? V in minus. This is fine. The op amp output is the gain times the non-inverting minus inverting terminal voltage. That's what I've written. And again, as you know, if let us say the gain tends to infinity, which means if you have an ideal op amp, as long as you know that the output is going to be finite, this has to. It is all the same. Fundamentally, it's asymptotic principality. I mean asymptotic equality. If this tends to infinity, this should asymptotically go to 0. And again, I mean, remember, sometimes another point of confusion. See, let us say I now take the same op amp and flip the signs. Make this plus, make this as minus. What will change in the expression? Huh? Yeah, I mean, basically the sign becomes minus A. Now I can still argue the same. But in practice, that is not true, because this entire thing is based on the assumption that my output quantity is finite and the fact that my output relation is this. Okay. Now remember, in practice, when I have this, the op amp is in positive feedback. And the moment you have positive feedback, output sort of blows up, and in practice it saturates. Correct? So if the output has saturated, do you think this relation is valid anymore? The relation is not even valid. So which means you can't make this argument. So what should be satisfied for you to make this, yeah, you should have negative feedback. Okay. So you should have negative feedback. If you have negative feedback and let us say one of the gains or GM something goes to infinity, then you can invoke this argument and claim that because the gain is infinity, output is constant, so the term multiplying the gain has to become 0. But that is valid only in negative feedback, wherein you can guarantee all the voltages and voltages are finite which means the relation you are assuming still holds good. The moment you are in positive feedback, things, as you know, starts to blow up. Either it blows up to infinity, which means this is not valid, or in practice things will saturate to supply or ground, which means this relation is not valid. Is this clear? So whenever you want to invoke this, understand you should have negative feedback, and only then you can do this. Okay, so now this is about, I think this is about common drain. So let's just do the last configuration. Again, remember we started with this goal. I mean, I know I can apply input output. There are three possible combinations for input output. We looked at gate to drain, that is common source. Gate and source we checked, common drain. Let's do the last combination, and that's pretty simple. We'll finish and wrap it. So which means now my input is at the source, output is at the drain, right? So for small signals, my gate will be ground. So again, I'll just look at the small signal picture. Let us say I have Vin applied here, and let us say some RD or something here, and let me ignore R0 for simplicity. So then tell me, what is the current drawn this direction? Small signal current, Gm times VGS. So this is minus Gm times Vin. Okay. Gate is 0, source is Vin, VGS is minus Vin. So what is the current that flows through R out in this direction? Plus Gm Vin. So what is my V out? That is the current Gm Vin times. So if you were to call the gain as V out by Vin, that is going to be Gm times. So looks like this also can provide voltage gain. Okay, and of course this is called the common gate. Because now gate is your reference potential. Now this also has a voltage, provides a voltage gain, but the practical, or one of the issues you might face is, remember I have ignored R0. So then what is the looking in resistance here, input resistance? Remember we saw the resistance looking into the source. When can you say it is 1 by Gm? If RD is very small compared to what? R0. I am saying R0 is infinity. So is that condition okay? If I ignore R0, I don't have to worry. So what is the input resistance now? Approximately 1 by Gm. So which means now, let us say, which means this is my input voltage source, correct? Let us say it has its own source resistance. The input impedance of my amplifier is 1 by Gm, correct? And for a large gain, I want to have a large Gm, which means the input resistance, will it be small or large? Yeah, that is not something you want, because then you see that only a small fraction of your input voltage appears. So that is one problem with this being used as a voltage amplifier. But the more common use for this circuit is the following. I'll just mention and wrap up. So let us say, let me remove this. So let us say here I push in current I in, small signal current I in. What is the small signal current I out? I in. So looks like my current gain is 1. What is the point of having something with a gain of 1? So again, this is used as a current buffer. See, once again the idea setup is the same. You have a current source which has its own output resistance. Now you want to make sure the entire current flows through RL. So you directly go and connect it. The output resistance of your current source will steal some current. So that is why we try to do the following. You try to make sure that this is given to a current buffer. Now remember, a current buffer has to somehow sense the entire current here. So what should be the input resistance of a current buffer? It should be 0, only then it can steal all the current. Then it will sense this current and copy the current to your load. Okay, so this is current buffer, and what kind of control source is a current buffer? So common gate, one of the main use cases is this, like a current buffer. And as you already know, the input resistance for this was how much? What is the R in here? If I ignore R naught, what is R in? 1 by Gm. So as you see, if you choose Gm to be sufficiently large, my input resistance will be small. So it acts like a better current buffer, or I would say this input interface is much suited for sensing current than voltage. Because the input resistance is small, it can be used to sense current much better than sensing voltage. So bottom line, common gate is, although it can be used as an amplifier, voltage amplifier, a better test use case is like a current buffer. So common gate is a current controlled current source. Similarly, if I had common drain, what kind of control source was it? Voltage control voltage source, right? That's a voltage. So let's stop here and we'll continue.